Okay, it looks like we'll get started. So good afternoon, everyone. My name is Erin Farley, and I'm a research associate here at JRSA. And it is my pleasure to welcome you to our webinar titled Significance Testing: Contingency Tables and Correlation. And this webinar is the third in our skill building series. Before we go any further, I first would like to thank our partners at BJS for helping us to make this webinar possible. And I would also like to cover a few logistical items. So we will be recording today's session for future playback. The link to the recording will be posted on the JRSA website. When you signed on today, you should have been prompted by an audio conference box like the one you can see on the screen. If for any reason you want to change your preferences, you can go up to the bar at the top of the screen and click on audio and go through to audio conference, and you can switch your preferences there. If you have speakers or headphones for your computer, there's no need to call in. Simply select call using computer. All telephones have been muted. If you would like to ask a question, please use the chat feature unless instructed otherwise. Please remember to select host. This session is scheduled for 1 hour. If you have technical difficulties or get disconnected during the session, you can reconnect to the session using the same link that you used to join the session initially. You can also call WebEx technical support at 1-866-229-3239. In the last 5 minutes of today's webinar, we will ask you to complete a short survey. The information you provide will help us to plan and improve future webinars and meet our reporting requirements. Okay, so the webinar objectives today are to describe the purpose of and how to interpret a 2x2 contingency table. We will focus on chi-square statistic and also how to run a cross-tabulation or contingency tables in SPSS. We will also describe the purpose of and how to interpret measures of association, specifically focusing on Pearson's correlation. And we will also show how to run a bivariate correlation in SPSS. We utilized a lot of sources to put this webinar together. However, the primary source is listed at the bottom of this slide, and that's Paternoster and Bachman's 1997 Statistical Methods book. Okay, so jumping right in. So the purpose of contingency tables, also referred to as cross-tabulation, is to show the relationship between two or more categorical variables. Categorical variables include things like gender, male or female, ethnicity, Asian, white, Hispanic, place of residence, urban, rural, suburban, responses like yes, no, and things like grade, A, B, C, D, F. Crosstabs, or contingency tables, are utilized when we are interested in learning if one variable is related to or depends on the distribution of another. By examining the joint distribution of two variables, we can determine if there is a relationship between them. A joint distribution refers to how the two variables are distributed together when we consider them simultaneously. Okay, so next slide, 2x2 contingency table. So here is just a very quick example. This is gender of victim by nonviolent or violent crime type or victimization type. There are several types of chi-square tests depending on the way the data was collected and the hypothesis being tested. For today's webinar, we will be presenting an example of the simplest case, a 2x2 contingency table. This contingency table includes the joint distribution of two measures. Already mentioned the sex of the victim, which is male or female, and the type of the victimization, which is nonviolent and violent victimization. In the lower right-hand corner, you will see that the total sample size is 200 cases. These cases were randomly selected from one state from the 2013 NIBRS victimization segment. For a 2x2 contingency table, there are a total of 4 cells that correspond to the joint distribution of the categories, and you can see those outlined in blue. Cell frequencies are, you can see under female, 54, 53, male, 67, and 26. So before I go any further, though, I wanted to take a moment to establish a null and alternative hypothesis. Our two measures of interest, again, are sex of victim and nonviolent or violent victimization type. Our null hypothesis is that there is no relationship between these two measures. And while everyone on the phone, or sorry, on the webinar is probably well aware of the complexity of violent crime and victimization by gender, for example, that males are more likely to be murder victims, females are most likely to be victims of domestic homicides and sex-related homicides, etc. For today's purposes, we are utilizing a general violent, nonviolent categorization. So as part of this exercise, let's just hypothesize that in general, females are more likely to be victims of violent crime versus nonviolent crime. Just to describe the table further, beyond the cell frequencies, there are row marginals highlighted in yellow, and these correspond to the total number of cases or frequencies found in each of the row categories. The sum of the row marginals equals the sum of the column marginals. Here, again, you can see the column marginals at the bottom of the table. These correspond to the total number of cases found in each of the column categories. Again, the sum of the column marginals equals the sum of the row marginals, which equals the total sample size, which is 200. A general rule to follow when interpreting contingency tables and calculating percentages is that if you can distinguish between the independent and the dependent variables, the independent variable should be positioned as the column variable. Now let's take a moment to look at the joint distribution of each cell. How many females were victims of violent crime among this 2013 sample? We can see that there were 53. How many were males? 26. However, one must be cautious when interpreting the numbers because the sample size between males and females differs slightly. Now, in other examples, the sample size could actually, the sample differences between the variable of interest can be quite different. And so in order to get a better sense of what this distribution means, one must look at the percentage distribution across these two groups. So this is the same exact table as before, only now there are also percentages. So this shows you that while violent crime or violent victimization represents approximately 40% of the victimization type among the sample of 200, females were more likely to experience violent victimization than males. Here I am looking across the violent crime row, 50% approximately for females and 29% for males. Now that we have examined the joint frequency and percentage distribution, how do we determine whether this difference indicates a relationship? That the pattern we see is not by chance. Another way to phrase it is to ask, how large does the percentage have to be to claim that the null hypothesis is false? To answer this question, we turn to the chi-square statistic. Assumptions of chi-square. So the data used should be frequencies, not means or proportions. Categories are independent and they do not overlap. You must have an expected count of at least 5 in each cell, 5 cases in each cell. So if we go back to our prior slide, we can see that that is not a problem. We have 54, 53, 67, and 26. Also, large samples mean large chi-squares, thus making it easier to find a significant chi-square. Sample size in this case matters when using the chi-square statistic. Okay, chi-square test of independence. So while we won't go into the equation or how to calculate by hand, I do want to take a moment to clarify and talk about observed cells and expected cells. So the objective of a chi-square test of independence, which is referring again to that chi-square statistic, is to determine whether the observed values for the cells deviate significantly from the corresponding expected values for those cells. So what this procedure does is that it not only takes the observed distribution, which is what you have, it calculates what the expected distribution would be if there was no relationship, and then determines the difference between what you have and what would be expected if you did not have a relationship. And so that value is utilized to calculate a chi-square statistic. Okay. So moving on, just to show the number of steps and output that you will see if you calculate a chi-square statistic and utilize cross-tabulation in SPSS. So here you would go, these are just snapshots. You would first go to Analyze, Descriptives, and then Crosstabs to get the small box that you can see on the screen. So within this Crosstabs section, you can see the list of variables to the left, and you can see the first small box to the right, the upper right side, says rows. In there, I have put violent, which is that violent dichotomous variable, and then columns is the next one, and you can see my variable there that represents the victim sex, female or male. And so this is a reminder that if you do know your independent variable, you want to put it in that column section right there. Now on the right side, you can see that there are a number of additional boxes, statistics, cells, format, and style. So if you click on statistics, this is what's going to pop up, and you want to check the chi-square box. Okay, and there are a number of other options that you can select as well while in here, and ones that are specifically relevant to nominal and ordinal measures, but we're just going to focus right now on the chi-square statistic. Okay. The next one below is cells. So if you click on cells, this is what's going to pop up, and you can see that there is counts, observed, expected, and you can hide small counts. You can do percentages, row, column, and total. So for right now, I clicked observed, and I clicked the column percentages. Okay, so here is an example of output that you would see based on the steps that I have gone through. And you'll see 3 different tables. The first table titled Case Processing Summary, you can just see it really just lists your valid cases and then your missing cases. I don't have any missing cases. So all 200 of my cases, which are individuals, are included in this analysis. The second box shows the joint distribution, and this should look familiar. It was the table that I had presented earlier. So when thinking how to interpret these percentages, you should say, Among women, 49.5% were victims of violent crime. Among males, 28% were victims of violent crime. Examining the third table, titled Chi-square tests, we are given a variety of statistics to interpret. For simplicity's sake, we will only concern ourselves with the first row of statistics, the statistic test labeled Pearson's Chi-square. So first we see that the value is 9.692. We see that the degrees of freedom are 1, and the degrees of freedom are calculated by the number of columns minus 1 times the number of rows minus 1. So that would be 2 minus 1 times 2 minus 1 equals 1. Moving across to the significance test, we see that the Pearson chi-square has a significance value, or a p-value, of 0.002. So using a 0.05 as our alpha level of significance, we can see that the 0.002 falls below that, meaning that we would reject the null hypothesis. If, say, the chi-square was 0.074, that would fall above our 0.05 significance level, and we would fail to reject the null hypothesis. What is also included at the upper right-hand corner is the syntax to run this analysis. You can kind of see a little bit of it actually at the top of the excerpt from the SPSS output, but there are a couple things that you can do. You can actually, when you are pointing and clicking in that table, let me see if I can go back a little bit. There you go. So if you have this table, you have selected your measures for the row and the column, you can actually look down, and next to OK is paste. And so you can actually paste the syntax into a syntax file and save that as a way to remember exactly what you had done. Okay, so this is just an extra example of output that I did want to show, and this includes the expected numbers, expected cell frequency if there was no relationship. So you can see that underneath count, you can see expected count, and that is both if you're looking in the violent row under 0 and 1, and then it also has all the percentages. So what I did is I went back and I clicked on that I wanted columns, I wanted rows, and I also wanted totals. So what this does is it gives you a lot more information and may be useful if, let's say, you don't know which measure is going to be your independent or dependent variable. If you are just, utilizing cross-tabulation for exploratory purposes, you would want to maybe look at all the percentage distribution both ways. And so this can be at times confusing. So one way to look at this is to always focus on, if you are, let's say, looking at the violent row, you would look at percentage within violent. So I would say something like within nonviolent victimization, within those events that were nonviolent victimization, 45% of them involved females and 55% of them involved males. And so you can, if you look at the total percentages, you can see that 100% along that row. That could be a guide as well to help you understand which percentage you should be utilizing to interpret based on what your variable, your reference variable, or your variable of interest is. So how to present findings. So we sort of went through the steps of how to create, conduct an analysis, output of SPSS. So let's say you have significant findings like we had. How would you actually put them in a report? Here is one way that you can do that. A chi-square test of independence found a significant relationship between gender and violent crime victimization, with females more likely to be a victim of violent crime than males. There you have the chi-square equals 9.692, and then the significance level, or P, less than 0.05. Depending on format, some places do also include degrees of freedom, so it may change, but this is a pretty standard way to report cross-tab findings. Okay, so moving on to measures of association, correlation. So measures of association refer to a wide variety of coefficients that can measure the statistical strength of the relationship on the variables of interest. These measures of strength or association can be described in several ways depending on the analysis, and today we will focus on the most common one, and that's Pearson's R, or Pearson's correlation. It's important to note that correlation does not indicate causation, and the direction and strength of an association or a correlation between two variables can be determined by using this coefficient. And I did want to include the equation for anyone who is so inclined to look it up and calculate it by hand, but today we will be using SPSS. So Pearson's R is also referred to as Pearson's correlation. If you hear people refer to zero-order correlation, bivariate correlation, these are all sort of interchangeable. So a Pearson's correlation attempts to draw a line of best fit through the data of two variables. And the Pearson's correlation coefficient R indicates how far away all these data points are to this line of best fit. It also assumes a linear relationship, as well as no significant outliers, and that variables are approximately normally distributed. However, this formula does perform well even when assumptions of normality are violated, and has been used when one variable is discrete. But the original purpose, main purpose, is to use continuous variables like age, temperature, things like that. So the correlation, the R, coefficient R, ranges from a -1 to a 1. 0 indicates no relationship. 1 indicates a perfect relationship. Now the plus and the negative indicate the direction of the relationship. So you can have a positive or a negative relationship. A positive relationship indicates that as one variable increases in value, so does the other one. And then a negative or inverse relationship indicates that as one value increases, the other one decreases. Here are just a couple examples. If you were to plot your data on a scatter plot. So here you can see the first one, the R is a -1, and right below that, the R is a +1, and those indicate perfect relationships. In the middle, you have an R that is a -6, an inverse relationship, but a moderately strong relationship. And then you have below that, a 0.3, a positive 0.3, indicating most likely a weak but positive relationship. The third column involves the R equaling 0, but looking slightly different. But both of these represent no relationship between the two measures of interest. Now, I have included a box to the right that provides some guidance on how to interpret the coefficient. This is important to note that this is just guidance. It does change depending on your reference and your standards. And so this may be something that in your own agency you want to determine sort of what is the deciding sort of breakdown preference for your agency. So here I just wanted to include that around 0.3 is considered a weak relationship, around 0.5 is a moderate, and around 0.7 is considered a strong association, a strong relationship. So I also wanted to include a example of a correlation in SPSS, and to do that I wanted to start with just a frequency of the two variables of interest, which include age of victim and then victimization hour. And this is a histogram of both of these variables. And if you remember, one of the recommended or one of the assumptions of utilizing correlation is that the measures were normally distributed. So here you can see age of victim fits that pretty well, and victimization hour is not as clean, but is roughly normally distributed as well. So these are two adequate measures for this purpose. As a side note, I want to add that I completely made up victimization hour. So the data that I pulled did not have another good continuous variable available beside age of victim. So I made this one up, and you'll be able to really see that when I show the results. So it's a little fudged. But the next slide shows hypothesis testing again. So the null hypothesis, no relationship between age of victim and time of victimization. The alternative hypothesis is that there is a relationship between age of victim and time of offense. And so what I did, just again as a reference, is I used military time, so 0 to 24. So it is useful to plot your data on a scatter plot to get a sense of the quality of the data. Very good first step. So if you would like to do this, if you have SPSS, you would first go to Graphs and then Chart Builder, and this is what you will see when you click on that. If you look at the lower left-hand area of the box, you will see that it's highlighted in a dark gray, scatter. And so what I did was I clicked on that, and I actually clicked on the very first box in there, in that option that has eight different types of scatter plots that you can pick. I picked the first one, which was called Basic. And then this is, once you clicked on this, it would pop up and look something like this. You have an x-axis and a y-axis. So my preference is to put the, again, the x-axis, utilize that as the, put the independent variable there if, again, you know what it is. And so I utilized, let me put that, I utilized the age of the victim as the x-axis, and you can see the list of variables to the left of that, and that's actually just a drag and drop function, so it's really easy. You just drag victim age over to the x-axis, and then I dragged hour of victimization to the y-axis. I went down, I pressed OK, and then this is the plot that resulted. So here you can see just how perfect it is, which is probably not likely, but again, fake data is useful when you get to create it. So this is how I created it. It shows a tight cluster of data points indicating a positive relationship between age and victimization hour. So as age increases, victimization, and remember this is military time, so as it gets higher and higher, it's actually later at night. So victimization is likely to occur later in the day. Okay. So after examining that, so we would, conclude that we see that definitely something is going on. But let's find out if that is a significant correlation. So moving to bivariate correlations, and again, you would go to Analyze. You would go to click on Correlate, and then Bivariate. And this box that you see in front of you, that's going to pop up. And then here you can also see that there is no column or row selection. They are just all put together under variables, and that's because you will actually see them. They will pop up and create, well, they'll pop up in both the row and the column. And here you can see under correlation coefficients, I have clicked Pearson. So once you press OK, you will see something like this. So again, you can see, as I had mentioned, age of victim is both in the column and the row. Victimization hour is also in the column and the row. And where they hit each other, the same, so victimization hour lines up with victimization hour. There's really nothing there. So you're looking at the other two, which in this case, because it is a 2 by 2, are identical. They're telling you the same thing. If you had more measures, you know, you would obviously have more to look at, but here they reflect each other. 0.971 is the Pearson correlation, and the significance level is 0.000. So the way to interpret that is that we do have a significant relationship, positive, and actually with a correlation coefficient of 0.971, quite strong. So here, if you wanted to present that, there's a couple of ways that you can present this information. Again, there are different agency preferences, but this is kind of standard language. You could say that the correlation between age of victim and time of victimization was found to be strong and statistically significant, and then you would include the R coefficient and the significance level here. You know, you could say P is less than 0.05, but we have such a high significance level, it's 0.000, that I actually included P is less than 0.01. And then the next sentence is, the older the victim, the more likely they were more likely to be victimized later in the day. Or you could say the results from a bivariate correlation analysis reveal a strong and statistically significant positive relationship between age of victim and time of victimization. So if it was, let's say it was not positive, but it was a negative or inverse relationship, it may be something like the age of the victim, you're younger and you're more likely to be victimized later in the day. So that is something that you may see. Just to take a side note to highlight the correlation, that 0.971 is actually quite high and could actually indicate a high level of collinearity if you were going to be utilizing these measures in more advanced statistics. They could possibly impact your findings. And so, and even some would actually recommend to flag values that actually are 0.8 or higher. So these are values that you may actually want to look at, you know, what is the measure and what are they measuring. So here we have age and hour of victimization, but you may have, for example, something like number of hours studied and grade or something like that, to which they are actually measuring so closely, they're measuring the same thing, then you would not need both of them in the same analysis, or they may be negatively impacting your findings in a more advanced analysis. This is also something that's important if anybody has handled you know, creating constructs. You're utilizing multiple measures and combining them to create a construct. When you have very high collinearity, again above 0.8 or above 0.9, this is something that you may actually want to dig further into and examine to see what is going on and how that might be impacting your construct or your results. Okay, so that was the presentation. So I want to take a moment to answer any questions that anybody may have. Let me see if I can pull up the chat section. Okay, yes, a copy of this PowerPoint will be made available. Actually, the webinar itself and a copy of the PowerPoint. And so just to give people time to see, think about any questions that they may have, I did want to highlight the topics that we will be presenting in the future, which will be simple linear regression, multiple linear regression, logistical regression, displaying data, and exploratory data analysis. Okay, so we have a very good question from Lynn. How do you handle zeros in chi-square tabled cells? So that is something that I actually, let me go back, did not highlight. Let me see. Here we go. So so we focused on Pearson chi-square, but if you did have issues where you had, and actually the threshold is 5. So if you had 5 or less cases in your cells, in your frequency cells, that would kind of be a red flag to which you would want to refer to Fisher's exact test. And you would want to utilize that. So it's important that if you do have small n sizes in your cells, to be aware of that. And when thinking about utilizing crosstabs, the larger the categories or the variables you use, like for example, we did highlighted a 2x2, but the larger you get, the more challenging it may be, A, to interpret the data, but then you're also creating an opportunity where you may have empty cells, which is going to be create challenges for interpreting your data. So I would recommend, thinking about the categories, sort of values you have in your data, like a 2x2, a 5x5, something like, once you start getting into a 10x2 or, 10x5, it seems to get a lot harder to actually interpret the data. Yes, so nominal, so you can utilize cross-tabulation for both ordinal and nominal variables. So nominal variables are variables that cannot be ordered, so they are like gender, male or female, versus ordinal variables. It could be something like a Likert scale or, a grade. So A to F could actually be ordered. And so those both can be utilized and examined within a cross-tab analysis. Did that answer your question? Yay, okay. Any other questions? So I think just as an aside as well, there are a number of ways to utilize crosstabs and correlations that we didn't talk about. We really just wanted to take a moment today to focus on 2 specific aspects of it. But there are other values like Fisher's exact test. And if people are interested in that, we do have a survey at the end of this PowerPoint for you all to fill out. So hopefully you would have a chance to say yes, you want to learn more, and also feel free to email me or Stan to say, hey, we want to learn more about Fisher's exact test, because those are the things we like to hear so that we can provide webinars that are most useful. Any other questions? Okay, great. I'm going to then open the polling. Let me see if I can do this right. And, we would appreciate your feedback, so please take a couple minutes and fill it out. Okay, thank you so much.